In today's class, we are going to see about hysteresis. We are going to understand in detail about hysteresis. So for this, I'm going to share. Okay, so now just open your note and try to follow the instruction which I'm going to give now. Okay, so today's class is about hysteresis. Hysteresis. Okay, this is the word hysteresis. What is meant by hysteresis? We are going to see. So hysteresis is actually derived from a Greek word, Greek word hysteros, which means delay, which means delay. Like this, a proper definition, if you need, you can write like this: lagging of magnetization, lagging of magnetization behind magnetizing field, magnetizing field. So this is a small definition you can see. Actually, hysteresis is nothing but it's a graph which is plotted between magnetic field and magnetic flux density. So graph plotted between magnetic field and magnetic flux density. Magnetic flux density. So to understand about hysteresis, so we are going to plot a graph. So let me draw the x-axis because already y-axis I have drawn already. So this is x-axis and y-axis. So this is x-axis, you have the h, and y-axis you have the magnetic flux density, capital B. Okay, so actually we have four quadrants now: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So this is minus h, and similarly this is minus B. Okay, so for plotting this graph, we are going to make one experiment. Okay, so for this, let us take a ferromagnetic specimen like this. So I'm going to consider a ferromagnetic specimen, that is iron material, and I'm going to place in a magnetic field. So it is placed in a magnetic field. So with the help of a digital meter, so this is a digital meter supposed to be. So I have a knob wherein I can adjust the magnetic field, like fan regulated 1, 2, 3, 4, 5, like this. Different Gauss values will be there. So 1, 2, 3, 4, 5 Gauss. The unit of magnetic field is Gauss. So first, uh, the initially this will be the origin O. Here B is 0 and H is 0. When the magnetic field is increased, what will happen? When the magnetic field is increased, what will happen to the magnetic flux density? Magnetic lines of force will be generated, so magnetic flux density also increases. Magnetic flux density also increases. So this can be plotted. So I am just keeping the knob to 1 Gauss. So here also I can mark this is 1, 2, 3, 4, 5, and 6, because this is a graph, so I can easily draw the graph. So this point is 1, this 2, 3, 4, 5, and 6 Gausses. Likewise, I have in a negative direction minus 1, minus 2, minus 3, minus 4, minus 5, and minus 6. So 1, 2, 3. So all are negative values: minus 2, minus 3, minus 4, minus 6. That's all. I've just written the values now. Now, when I increase the Gauss value to 1, what happens? There will be a corresponding value of B. So this is H and this is P. Okay, when I keep the magnetic field to be 1 Gauss, the magnetic flux density will be somewhere. Okay, so the corresponding value I can mark here. Okay, let us mark the values. So for when H is equal to 0, B is equal to 0. When 1 Gauss, magnetic field shows some value. For 2 Gauss, the magnetic field shows some value. For 3 Gauss, it shows some value. For 4 Gauss, it shows value. Let me stop at 5. Okay, let me stop at 5. Now what I will do, in order to complete the graph, I will join the lines now. Now I'll join these lines. Okay, this is the maximum line point. So this can be marked as H max, and this can be labeled as A. So what I've done, so this is actually step 1. So in step 1, I can see that in step 1, I have done magnetization. I have applied magnetic field to the material. So this magnetization continues from OA, OA until A is the maximum limit. Okay, magnetization has been done. So as I increase H, B also increases. Okay. As H is increased, B also increased. So this is step 1. Then in step 2, I will make demagnetization. Demagnetization I am going to do. What I will do, I will make H2 equal to 0, and what will become to B? This is my question. So I will decrease the H. As I decrease H, B also will decrease and leading to 0, and what will happen to B? So when I do this job, I could find that as H increases, B also increases, so decreases. And but now this B will not go to 0 but goes to a point somewhere in the y-axis. Let it be point number B, point B. So we have AB. So now we have AB. This A region OB is called as residual magnetism because there is some residue of magnetization which is present inside the material. This residual magnetism is also called by the name retentivity. Retentivity. But in order to understand about the hysteresis, I don't want this residual magnetism and the retentivity. Okay, what I will do is I have to remove this residue. For that, I will go for the next process, which is called as step 3. Step 3 is once again magnetization is being done. But this time, this magnetization will be done in a reverse direction. So I'll take this same ferromagnetic specimen. Now this ferromagnetic specimen will be kept in a magnetic field in a reverse direction. South will be this side and north will be this side. Okay, now I am applying minus H, that is negative. This is plus H, positive H. Okay, so what happens now? What will happen? Now, as I increase the magnetic field, the, this retentivity tries to reduce. So this can be indicated here. Okay, it reaches a point minus 2 in the x-axis, so which is a negative magnetic field which I have applied. So let me give a label here, which is C. This is C. So here in negative magnetization, OC is called as coercivity. Coercivity, which is nothing but the negative magnetic field which is applied to the material. So okay, so here what we have done, so H increases. So the B retentivity completely vanishes. Retentivity is completely vanishes. Now in step 4, my next step 4, next is alternate demagnetization and magnetization I am doing. Now I will remove the magnetic field. So magnetic field on, magnetic field off, magnetic field on, magnetic field off now. So now I'll get demagnetization, then I'll complete the loop. Okay, then again magnetization, and finally I can complete the loop like this. So this is BCD. The point on the y-axis, this is E. The point on the x-axis will be F. So hence we get A, B, C, D, E, F, and A, which is called as hysteresis loop. Which is called as hysteresis loop. The area inside the hysteresis curve, the area inside the hysteresis loop or a curve is called as, so let me give a multicolor. Okay, the area inside the hysteresis curve is called as energy loss. The area of the hysteresis loop gives me the work done by the ferromagnetic specimen, gives me work done by the ferromagnetic specimen, and from this we can get the information about energy loss produced by the material. Energy loss produced by the material, and it is one of the experiment in our laboratory. So when you get back to the campus, we will work out with the experiment of BH curve. So these are the steps involved in getting this energy loss for a particular material. Okay, so this is hysteresis. So using this, what a simple definition you can frame. The simple definition goes like this: a cycle of magnetization and demagnetization, magnetization and demagnetization leads to a ferromagnetic specimen leads to an energy loss produced by the specimen, is known as hysteresis loss. Like that you can conclude. Okay. The enclosed curve ABCDEFA is called as the hysteresis curve or a hysteresis loop. Okay. So from the shape of the hysteresis loop, we can say whether the material is hard magnetic material or soft magnetic material. For this, I am going to frame a difference between. So now just open your note. Hope you are writing, I think, and I am also conveying you the message that this portion will not be handled once again in the campus. Okay, when you are back to the physical mode offline classes, only based on the portion completed, we'll proceed further only. We won't take the topics which I've already taken in the online sessions. Okay, so this I am making you clear now. Now we are going to see a difference between soft magnetic material and hard magnetic material. Difference between soft magnetic material and hard magnetic material. So soft magnetic material, as the name itself easily says that the material the material can be easily magnetized as well as demagnetized. So what you will write for hard magnetic material? The materials are difficult to magnetize as well as demagnetize. Difficult to magnetize and demagnetize. For soft magnetic material, you just require a minimum or a small field is enough, or a weak field is enough. Whereas hard magnetic material which require a strong field to magnetize and demagnetize the specimen. Next, let us discuss about the BH curve. So this is H and B. For soft magnetic material, The loop area will be narrow like this. Loop area is narrow. So in the case of hard magnetic material H and B, the loop area will be broad like this. Loop area is broad. The most important two parameters that has to be considered here is the retentivity and coercivity. Coercivity, high or low. Retentivity and coercivity, based on the information you gathered, whether it will be high or low in the case of soft magnetic material. What is retentivity and
Go,
coercivity?
ma'am.
Ah, so this retentivity is this portion, coercivity is this portion, between this portion. So this retentivity and coercivity will be low in the case of soft magnetic material, whereas this retentivity and coercivity will be high in the case of hard magnetic material. Okay, the next concept is to remember about permeability and susceptibility. Hope you remember what is meant by permeability. Tell me about permeability and susceptibility, whether it will be high or low. Permeability and susceptibility will be dash, and this permeability and susceptibility will be dash here. Tell me what to write here, high or low.
Ma'am, high in case of soft magnetic material.
So permeability and susceptibility value is good. High in the case of soft magnetic material because so they are so thin and they can easily permit the lines of force to pass through. And the materials also easily get magnetized in the case of soft magnetic material. What you have said is very true and good. And this for hard it will be low. Okay, this is the one thing you can have to write in a reverse manner. Retentivity and coercivity low, permeability and susceptibility high. Okay, so next we'll have a discussion about the sixth point. So this point actually, I'm just going to give you the examples. So examples of soft magnetic material and examples of hard magnetic material. So hard magnetic material mostly alloys of iron we can take. Okay, some steel. Example: carbon steel, chromium steel. Then you have the famous NIF. Then alnico. Okay, so these are some of the examples. Here, Kunif is nothing but copper, nickel, ferrous, and alnico is nothing but aluminium, nickel, and cobalt. So this combination will make a hard magnetic material. Soft magnetic material, I think you remember, iron. Okay, alloys of iron mostly are referred to as soft magnetic material. Even nickel and cobalt
Nickel,
nickel and cobalt are also can be considered to be soft magnetic material because they easily respond to the applied magnetic field. Okay, so this difference between what we have seen, no, and in the end we have to conclude with the applications. Where do these soft magnetic materials are used? Okay, and where do these hard magnetic materials are used? So mostly soft magnetic materials are used as temporary magnets. They are used as electromagnets in the transformer cores, even in the storage. Like example, we have RAM, that is random access memory, ROM, read-only memory, and we have pen drives. Then we have USBs, then memory cards. So in that case, soft magnetic material will be used. The hard magnetic materials, its applications are enormous, mostly in motors, then generators, So wherever you require more amount of magnetic field is required, hard magnetic material can be used in such cases. Magnetic flux meters, transportation, in those cases, hard magnetic material will be used. So mostly they will be used as permanent magnets because they have the storage of energy which is enormous, whereas compared to the soft magnetic materials. Mostly they'll be used as permanent magnets. They are used as temporary magnets. So electromagnets are temporary magnets. So with the help of this difference between, you can attend 2 mark question as well as 8 mark questions. So 8 marks comes under the part B category. Hope you will write the descriptive type of examination only, I think. Okay. So so we have to focus on the descriptive type also. So for 2 marks question, minimum of 4 points is required to write in the paper because each point carries half a mark. In bigger question, at least 8 points. So I have just listed out some seven. No, even the fifth point can be split up into two. Permeability is high. Then sixth point, the susceptibility of soft magnetic material is high. Like that, you can split into two and you can write in the examination. Okay, clear, students? So what we have seen is about hysteresis today. So hope you have taken the record of the hysteresis information today. So I'm just going to show the PPT also related to the hysteresis. So hysteresis, so plot of H and B, so OA, the complete hysteresis loop, the area gives you the energy loss, lagging of magnetization behind the magnetizing field, from where it has been derived, Greek word hysteros, which means delay, and then a ferromagnetic, this is the definition for the hysteresis loop for a curve, and a ferromagnetic material is made to undergo through a cycle of magnetization. Variation of B with respect to H can be represented by a closed hysteresis loop for a curve. Okay, so for each point, I'm just showing you these are the points. Then what is OA? What is OB? So this is retentivity. This is coercivity. Then we have the steps involved. How you are making the complete loop, the area enclosed by the loop, work done on the ferromagnetic specimen gives out the energy loss. Then the difference between we have seen just now, hard magnetic materials and soft magnetic materials, and their applications also I have just given you at least three applications. If you remember for each magnetic material, it will be very good. Okay, and the examples also three you remember. Okay, iron, silicon alloys, ferrites, and garnets are the missed examples which I have given, which I have not said you. And in hard magnetic materials, I have covered you carbon steel, chromium steel, and punif and alnico. You can also add punico, that is copper, nickel, and cobalt also.